Swayam Prabha. Digital India. Educated India.
Welcome to the fourth video of week 3. We started with the block force method and we looked at one of the cases using this method. Now, we will talk further about that case. We saw that the strain that we get in the beam, now here the strain in the beam, because the strain is found out only in the beam, we are denoting it as epsilon b, but it has only epsilon 0 component, which means only the axial component under the extensional case, and that is equal to EAC by EAC plus EAB multiplied by epsilon p. And if we recall, we got the same expression for the pure extension case in previously also when we are dealing with the Euler-Bernoulli beam based method. So, the block force assumptions does not alter the result here. Later on we will see that when we talk about bending, the result gets changed. Now, before going to bending, one more thing, it is finding out the displacement because of this kind of strains. So, again it is the same thing. If we find out the strain, because the displacements, because the strains are same, the results would also be similar. U would be 0 when my x is less than x 0 and u is going to be EAB plus EAC multiplied by x minus x 0 when it is and u is going to be multiplied by LC when x is less than x is greater than x 0 plus LC. So, here we are finding out the strains and we are integrating the strain as we did before with the boundary conditions, and we get our displacements at different parts of the structure as this. Now, we will go to the next case where we will see a bending effect. So, this is a pure bending case, and again here the actuation is opposite. If it is plus here, it is minus here, if it is minus here, it is plus. And so, if the top piezo tries to contract, it will if the top piezo tries to shorten in length, it will experience a tensile force and the top part of the beam will experience a compressive force. On the other hand, because the actuation is opposite, the bottom part of the beam will experience a tensile force and bottom piezo would experience a compressive force, and that would give to a bending in this fashion. In the contrary, if the actuation is just opposite, then the top piezo would experience a compressive force and the top part of the beam would experience a tensile force, and at the bottom part it would be opposite. and in this case it would result in this kind of bending, and everywhere the force is just F. So, needless to say, when the loads are opposite, I mean when these forces are opposite, it will the net effect on the net force is 0, but it will induce a bending moment. So, it is a bending case. So, again we will apply the same logic, we will find out the displacements here, and we will apply the compatibility condition that the displacement at the piezo and the displacement at the beam are same. But here, because it is a bending case, the displacements of the beam along Z is not same. So, the displacement here and displacement here is different. So, the displacement here should be is equal to the displacement here at the piezo, and similarly the displacement here at the beam should be is equal to the displacement here from the piezo side. Let us assume that these forces are inducing a bending moment M. Now, because of that bending moment M, the strain here is M divided by IB, moment of inertia of the beam, multiplied by this distance, the distance from the middle to the top. So, it is TB by 2. So, if the entire thickness is TB from Z equal to 0 to the top part of the beam, it is TB by 2. So, M by EIB into TB by 2 multiplied by 1 by EB, that is our strain at the top with a negative sign as per our convention. Now, bending moment, if the force here is F and if the force here is F, the bending moment is F into TB. So, our bending moment is F multiplied by TB. So, we can replace M by F and the expression becomes this. So, that is our strain at the top fiber of the beam. If the strain there is this, the change in length of this part of this portion of the beam is delta LB is equal to that strain multiplied by LC. So, which is this. Now, similarly, we have to now consider the change in length of the piezoelectric actuator. So, the piezoelectric actuator is under a force F. Again, applying the same procedure that we did before, we can find out delta LC, and delta LC here is this. Now, again we can equate these two, and after equating we get our F as this. Okay, solving we get the force is this. Here this expression is further compacted in terms of EIB, EIC. EIB is the moment of inertia of the EIB is the bending stiffness of the beam itself, and EIC is the combined bending stiffness of the two actuators. So, while calculating the bending stiffness of the actuators, we make some simplifications here. If this is our beam section with the two actuators, then while finding out the moment of inertia with respect to the midline of the beam, what we do is we first find out the moment of inertia of the piezo patch with respect to its own centroid, and then shift it here. Now, the moment of inertia with respect to its own centroid for a piezoelectric patch can be negligible when the patch thickness is quite small. So, under that assumption we remove that term and retain only the term which we get by shifted to the midline of the beam by the parallel axis theorem. So, only we retain that term, and then again it can be written as this. So, with these two we can write the force in terms of the block force as this, and again there is a relation between the EIB and EAC, and from that we can again rewrite the expression in terms of EAB and EAC. After that, we calculate the actuation moment. Actuation moment is the actuation force multiplied by TB, and from that we get this expression for the actuation moment. So, this is our MBL block moment, because FBL into TB is our block moment. So, moment is equal to force multiplied by that F multiplied by the TB, and MBL is equal to FBL multiplied by the TB. These are block moments to say. So, this we can term as block moments analogous to block force. And again we can replace EIB and EIC by EAB and EAC. Now, for pure bending actuation, the actual axial beam strains vary linearly across the beam, and therefore, we can write the strain as this. So, this is our strain epsilon B, and epsilon B, as we know, it is, we can find out from the standard formula, moment divided by EIB into Z, and that gives us our the strain at any Z from these findings. Now, from that we can find out the moment at the top surface of the beam. So, if this is our beam, so at here it is TB by 2, here it is TB by 2. So, this is the beam without showing the actuator. If I want to find out the strain here, we just replace Z by minus TB by 2, and we get the moment here in terms of both EIC and EAB. Similarly, when we want to find the same thing at the bottom surface, we just replace Z by replace Z. Here we replace Z by TB by 2, and we get this, and for here we replace Z by minus TB by 2, and we get our strains at the bottom surface. So, strain here at the top surface and strain here, strain here at the bottom surface, and we get the two strains at the two extreme surfaces. Again, for some extreme cases we will see how it behaves. So, when we have our EIC much greater than EIB, in that case our block moment is 0. So, if we look at this expression, this term becomes 0 when EIC is much bigger than EIB. So, this term is almost 0. This term is almost 0 means the piezoelectric patches can expand or contract freely, and that we can see here. So, epsilon B at the top surface is minus epsilon P, and epsilon B at the bottom surface is epsilon P. In the reverse case, when EIC is much less than EIB, in that case the movement of the piezoelectric patches are almost constrained. In that case, the moment is equal to almost the block moment, and the piezoelectric patches do not experience any strain. Now, once we know the moments here in terms of the block moments or the free strains, we can find out how the beam deforms. So, this is how it is. We already saw how to solve these problems, and if we just follow the procedure, if we follow the governing differential equation, that is E I del 2 W del x2 is equal to m. Here we have to put the appropriate E. So, here we will put EIB, because we already know what moment the beam is experiencing, and in this method we do all the calculations for the displacement considering EIB. So, and m we know in terms of the block moment, we can write it in terms of the block force or the free strain also, and then we can solve the differential equation, put the corresponding boundary conditions and solve it. After solving it, we can see that in this region the slope is 0, in this region the slope is this, and in this region the slope is this. When finding out displacement, we see that in this region displacement is 0, in this region displacement is this, and in this region displacement is this. So, before concluding the discussion on this beam problem, we would see that the result that we get for the beam problem using the block force method would turn out to be somewhat different from what we get by solving the Euler-Bernoulli beam based technique, because here you are making an assumption. The assumption is that if we talk about this section only, it has a piezo at the top and at the bottom. So, when this bends, it bends in this fashion, and as per the Euler-Bernoulli beam, we saw that the top part, the piezo part also bends. Which means the strain is changing in the piezo part as we go along the thickness of the piezo. However, in the block force method, our piezo strains are same along the thickness. So, this variation we are ignoring in our block force method. So, that is why it gives some difference in the results. And in fact, if we see that if we want to make our piezo behave in such a way that its strain is same, that is not very much feasible physically. So, that is a big assumption in the block force based method, and that is why the result, although the result was same in extension, because in extension or contraction it does not matter, this kind of bending does not come into picture, but in bending case the results are different. Okay. Now, here the axial stresses are calculated in the same way the axial stresses can be calculated. So, in the first part of the beam where the actuator is not here, stress is 0. In the mid part, under the actuator part, there is some stress, and after that again the stress is 0, and similarly the strain is also 0 at the first part without the actuator, and then there is some strain, and then at the other part which is free from the actuator, again the strain is 0. And this is calculated here at the top part. So, if you want to be generic and write it in terms of any z, so it is mb by EIB plus EIC multiplied by z, and this is for top surface, and this is for any z. Now, similarly, we look into the case of unequal electric voltage. So, while dealing with Euler-Bernoulli beam, we saw the case when what to do when the electric voltages are not equal. Same situation comes here. The electric voltages may not be equal. In these two cases, in the using the same procedure, we decouple the voltage into V top and V bottom. V1 and V2, and V1 and V2 in terms of V top and V bottom are these. And then for the V1 part, this is the actuation force Fe, here E stands for extension, it can be extension or contraction as well. And similarly for the V2 part it results in bending. So, the corresponding force is Fb and the corresponding moment is m. And then from here we find out, we just superimpose Fe and Fb and we find out the force at the top F top and the force at the bottom F bottom. So, if this is our beam, this is along x axis and this is z axis, we have the piezo somewhere here maybe. Let us assume that the forces are in this form, but they are different. So, this can be written as F top, this can be written as F bottom, or vice versa, the sign also may change. And F top and F bottom, they are not same, they can be different in terms of their directions also, and magnitude also, by magnitude wise also they can be different. So, with that I would like to finish this lecture here. In the next lecture we will look at the other cases using the block force method. Thank you.